Hi everyone. Really exciting to be at this DeSci event. Like, it's so cool to see all of these people coming together. I'm Joel. I'm going to be talking about what we've been building with Ceramic and how it can be used for kind of creating a scalable open graph, which we can represent data in DeSci. So first of all, what do I mean when I say an open graph? It's kind of like a very diffuse, like not or abstract topic. And I think of it kind of like as a knowledge graph of the internet that is kind of open, living, and relational. So the data within it has relations among itself. We also have relations of like who authored what data and basically like the relationship between the people and the knowledge, like both of that. I think once we can start to have like an open graph like this, we can start doing like looking at the data and who contributed it and start to do like collective sense making. And I think this sort of system can be like a foundation for more open and collaborative science where it's not like locked into academia or some niche citizen science project, but like actually a lot of people contribute to it. And so I want to first look at some kind of properties that we need this kind of open graph to have. So the first is interoperability. We really need to be able to have multiple applications that can use the same data, and we can have multiple organizations that collaborate on the same data sets without any of the data being locked into any particular apps or platforms or organizations. And we want to be able to optimize workflows for different sort of use cases. So some people might have a project that needs just like querying the graph data directly. Some people might need to take that data, do some transformations on it, and kind of provide different views on top of the data. And we want composability. If someone creates a really useful data set, and you see that like, I can use that, but I need more things, you should be able to create a different data set that kind of like includes the previous one. And there shouldn't be like, you shouldn't need to like recreate things. And I think like if we have these properties, we can really start to increase the rate of innovation in open science and DeSci itself. Another important property is for us to have authenticity. So we need it to be censorship resistant. We don't want certain actors to be able to just like remove data from this graph. We want every action to be like authenticated. So we want signed updates to data, and we want secure timestamps. And what this gives us is that we essentially need the audit logs of like how data changed over time to be verifiable. And finally, what all of this kind of authenticity in the protocol would mean is that we can actually build reputations for authors. We can look at what their contributions and see kind of if their contribution was valuable and kind of give the people contributing reputation. So let's just put it on the blockchain. What can go wrong? Well, as many of you might know, like blockchains are not really scalable enough to deal with like web scale data. Like we're even running into issues with like only putting financial data on top of blockchains. So some systems try to solve this, but the main blocker here is really that blockchains favor strong consistency, and there's a good reason for that because like we want to be able to have financial transactions kept on the blockchain, and we want to limit something called a double spend attack. And for that, we really need every transaction to be totally ordered all the time. And nice things we get from this is like fund management, and we can fund public goods. We can get NFTs, which is super useful for like IP NFTs and other things that probably a lot of things with NFTs that we haven't really imagined yet. But yeah, we have this fundamental limit of like the block producer can only get so much data to the system because we always have to have one node that produces a block. And so can we scale blockchains for data? Well, there's basically two camps of approaches to this. The first camp is bigger blocks. So here we have like Solana, we have Celestia, we have Arweave. They basically just make the nodes that produce the blockchain really beefy and have various ways of providing security guarantees around that. And but even if you have larger blocks, like having a singular node that produces block, you still can't have like web scale throughput of your system. A little bit more better approach is taken by the proof of storage protocol. So like Filecoin, we have SIA, Storj. They essentially allow you to make an agreement with a node in the network to store your data. And you can kind of take a big chunk of data and you just give that to one or multiple nodes and have them store that verifiably. So that's great. We can now put like large data sets into blockchain systems. But we still have a problem, like if we want a lot of like data parallelism and produce a lot of data in parallel, we're still limited by the throughput of the block producer because we need to make this kind of agreement needs to be a transaction on the blockchain in order for it to be verifiable. And so what we really need is a system that is decentralized and also eventually consistent. So all data is not kind of ordered from the start, but and we can produce data in parallel, much more than like what a single node could handle. And I think we can achieve this if we build a system that has verifiable like audit trails. And I'll get into kind of how we do this with Ceramic. We want the data here to be composable. And the key insight of being able to build this kind of eventually consistent decentralized protocol is that we're not dealing with financial data. We're dealing with non-financial data, so like any other data that you don't use to make financial transactions. And that allows us to have this kind of eventual consistency because we don't need to protect against double spends in the same way. So I'm going to give you an overview of what we're building with Ceramic. So at the base layer, we have an event streaming system where we basically have verifiable event streams. We index those, and then at the top, we provide a GraphQL API to create and query data. So at the base layer, we have stream availability. And so essentially what we have here is independently verifiable event logs that any node in the network can connect and synchronize one particular log in the system and be able to know that this is the right, the log is, you have the integrity of the log without synchronizing the state of the entire network, which you need to do with blockchains. We're using DIDs, decentralized identifiers, which is a W3C standard for representing kind of decentralized identity. And this allows us to authenticate into Ceramic using any blockchain wallet that uses public key cryptography. And all this is synchronized over a peer-to-peer network, which essentially means that we don't have this kind of global state layer. And finally, to make this kind of complete, we're starting to design an incentive layer that allows you to kind of pay the network to be sure that your event streams are going to be available. So just very quickly, an event stream looks like this. You can create it by creating a Genesis event. You can make updates by having a signed event. And periodically, these events are anchored into the blockchain. And so you basically take the hash of the previous event, put it on the blockchain, and then you get like a verifiable timestamp. And so, of course, like if every event stream needed to make one blockchain transaction every time it's anchored, that's not really super scalable. But what we can do is just like take a bunch of updates from a bunch of different streams, build something called a Merkle tree, and put just one small proof on the blockchain. So we can actually make the throughput of the system really high, even though we only have like minimal blockchain interaction. Then on top of this, an indexing layer, basically taking the data that's in these event streams and building some stateful database table on top of this. So every node in the network will have their own kind of view of an index. And so it's not like a global consensus on the data, but rather like a local view on top of all the streams. In order to not have every node index all of the data in the network, which obviously wouldn't scale, we have data models. And these data models, I'll go into in a bit, but they have semantic descriptor objects. And each node kind of chooses which models that they want to index in the system. And that's kind of how we can achieve scale, because we don't need to care about the state of the entire network. And the interesting thing about using this event streaming architecture is that you don't necessarily need to use this, the indexing system that we're building. You could plug in directly to the event streams in the system and build your own indexes. Maybe you need some index that doesn't do GraphQL, but it does like a time series of some data that's happening in the system. I'm sure like eventually there's going to be a lot of different sorts of indexes on top of these sort of like event streaming protocols in Web3. And so the data models, they can be created using the GraphQL schema definition language. I'll give an example in a moment. And of course, queried using GraphQL. So it's like a very kind of intuitive graph interface to reading and writing this data. And the cool thing about having a data model that describes a data set is that any individual user, they will produce their own events and streams. Any user can come in and like write data to a data model, but you can choose like, oh, I want to index only a subset of users, or I want to index all users. So it's kind of like this open world data sets where anyone can write data to a data set. And this, I think, like really enables us to have much more like collaborative applications where people can just come and contribute knowledge. And so these data models, you can discover existing data models that have been created in the ecosystem, and then you can kind of take those, build data models that rely on other data models and compose them together. So an example of how this would look like, here we have a very simple example where at the top we have a proposal, and so you can get the author from the context. The proposal has a text, and the proposal has comments, and the comments is basically a relation to this other data model that also has a text, but it also includes an ID of a proposal. And so these are two different data models, but they kind of compose on top of each other. And the cool thing now is like once you as a developer has created these semantic descriptor objects and put that into your application, anyone with like an Ethereum wallet can just come and start writing data to the system without having to ask for permission. And just create a bunch of proposals, create a bunch of comments, and if you look at the particular proposal, you'll be able to query comments and vice versa. All right, so I think you covered most of the kind of meaty content. What you can actually do with this. So I think some of the exciting use cases of this is that we can create a semantically meaningful knowledge graph that is really collaborative. If we can capture claims and evidence and research questions and have anyone be able to contribute to that in real time, I think we can kind of totally change how we do science as an open society. And yeah, like really enabling and scaling citizen science to kind of like from like a niche thing to like a commonplace interaction for people. And final thing that I think is really cool, since all of the data in the system is verifiable, you have this audit trails of who contributed what, then we can look at that, run some computation on top of that, and potentially reward people that contributed in meaningful ways to various projects. So we can have this kind of retroactive funding of science, which I think is like really powerful. All right, that was everything that I wanted to cover. And so what I went through today is kind of the next iteration of Ceramic that we're working on. You can still check out the current version of Ceramic. We have a developer website, and you can join our community, our Discord community. Thank you all for listening. I think we have time for questions, yeah.
When will the next iteration be available?
So the indexing system that we're building, it's probably going to be available in the middle of the summer. Any other questions?
Can you explain the rationale again behind not having a global state for the graph?
Yeah. So there's this thing with the blockchain where essentially, in order to reach consensus, every block that's produced needs to be produced by a particular node. So in blockchain consensus, like in proof of work, the way you choose who produces the block is the one who is able to mine the block. In proof of stake, you basically have a random selection for who the block producer is every round or every block slot. But it's always like one node that produces the block, and that node gets to order all of the transactions inside of that block. And so you're limited by the throughput of this particular node. You can't get more throughput in the system than this one blockchain node. But if we have every piece of data be like an event stream, and users create their own event streams, like every user produces their own events, and that are put into like a user-centric event stream, then we can have nodes just like processing parts or like individual event streams and making sure that they're available. And then you get way more throughput because we're not limited by a central node in the network that needs to process everything. And so if you think about how Web 2 scales, even if you didn't have a blockchain, you could never scale, Facebook or Twitter having only like one server that's super big and processes everyone's tweets. That's just not going to work. And so instead, you have like a bunch of different servers that are in different states, but eventually they will reach the same conclusion if they've seen the same events.
Do you mind just explaining with that, like how does it work if two different people are trying to mutate the same data?
So in the system, every user produces their own event stream. So they produce their own documents, so they are kind of completely independent. And you could build a system that takes two event streams and modifies the same, or like you create some common state from two event streams. Generally, you would use something called a CRDT, a conflict-free replicated data type, to achieve that. That's not something we're building right now, but it's definitely something we have been looking into.
Got you. So main goal is just to enable high throughput. Anyone can publish data.
Yeah, and then having like a simple index system on top of that. So the indexer that we're building was basically a Postgres SQL table that we can do GraphQL queries on top of. Eventually, I think there's going to be different sorts of decentralized indexes on top of Ceramic. We're talking with Protocol Labs and the Graph and like different approaches to creating these indexes. Cool. Any other question? Yeah?
One more question. So how do you see the open graph that you guys are building in Ceramic interacting with other projects, like, for example, Lens Protocol, which is building a social graph?
Yeah. I think Lens Protocol is useful for, like, they're producing a protocol based on NFTs. And NFTs are great for kind of connecting to the financial ecosystem of blockchains. I don't think you can have a protocol where everything is an NFT, because you're going to have this limitation of a blockchain can't scale that much. But you can use the NFTs for particular things and essentially monetize the data using that. So I can't speak to like exactly their architecture, like how that would be relevant, but like NFTs in general are useful for like tying in and financializing data. Cool. Any last question? Great. Thanks all.